advised one of our undergrads on an REU there on white dwarfs.
Oh yeah, that's he invented that field.
Yeah. Did you overlap with Brian Sanders?
No.
Okay, he's one of our undergrads. He's one of the great things. So he did his bachelor's at Caltech, his PhD under Mike Jura at UCLA. What was it on? Some exoplanets.
Yeah, my thesis was on M-dwarf planetary systems before they were exciting.
Well, they're very exciting now.
Yeah, they are certainly now. They have an entire NASA mission dedicated to it.
And then after his PhD, he did a postdoc at Caltech and loves the Los Angeles area, and then went to Missouri State in Springfield. Very close, by the way, to the birthplace of Edwin Hubble, who also lived here. And although the house there blew up, did you ever try to visit where his house was?
No, but he was in
Marshfield.
Marshfield.
Yeah. So his houses here didn't blow up, but they're pretty much ignored, which is sad. And then he went on to a faculty position at George Mason. He's going to talk to us today about two planets in a protoplanetary or debris disk system.
Was that what I said the title was?
That's what I thought.
Oh, that's fine.
Oh, he's going to talk about the golden age of exoplanet discovery.
Yeah, so I will talk about one of those planets today in the debris disk system. Thank you all for having me. It's been a pleasure visiting the campus today and in all of the planetarium that you have here on campus. That was a very, very nice planetarium. And I'd like to thank Dr. Kilkoff for inviting me here to give this talk, which I put together just recently, and the obligation of the recent talks I've given. This, for me, is the end of a 2-week tour for various reasons, traveling, and so it's been a long couple of weeks. I'm probably sitting my counter here for a bit. So I am going to talk about the golden age of exoplanet discovery, but mainly what I've been working on. And just to acknowledge that this work really represents the work of many scientists, not just myself, but a number of my graduate students and undergraduate students, including Bryson Kale, who's my PhD student currently, William Metzko, who's a PhD student at George Mason, Jonathan Gagney, who's a former graduate student of mine, Peter Gow, likewise, and on and on. And I'd just like to acknowledge that some of this data that I'm presenting was taken with telescopes atop Mauna Kea. And as you may have seen in the news, trying to build a new telescope in Mauna Kea, and some people aren't very happy about it. So I want to acknowledge the very significant cultural role and reverence that the summit of Mauna Kea has always had within the indigenous Hawaiian community. And I'm very fortunate genuinely fortunate to have the opportunity to visit there and to conduct research. And just to acknowledge some work, some support I've received from NASA and the NSF. So, we all know that when stars form, the material left over from the formation of a star settles into a spinning disk. And this is just an artist's rendition, but we see real examples of these disks. These are called the Orion probelids, where we're seeing them in reflection behind from the reflection of Orion. So we're seeing them illuminated from behind. And this is exactly what we see. We see these newborn baby stars surrounded. Hi, how you doing, Karen? Good to see you.
Hey.
So we know that stars form in this way. We can see empirical evidence of their formation. And from there, we've taken some beautiful pictures with ALMA. These are not real pictures. These are sub-millimeter wavelength observations and imaging using interferometry, showing all sorts of varieties of disks around young stars, and now we're finding gaps in these disks, and as best as we could tell, these are sites of planet formation. So we think that with time, the material left over from the formation of the star coalesces into planets and often go through what we call a secondary disk or debris disk phase, where these protoplanets collide and fade over time, eventually leaving behind a new planetary system. We also see some great examples of these debris disks. So this is just one survey from one instrument on the Subaru telescope. I think this is Scaxeo, maybe? But a variety of debris disks where the gas in the leftover gas is gone. It's either been ejected or absorbed by the planetary systems, and we're seeing the effects that newborn planets are having on this construction zone of debris. Now, for those of you that have ever been in a neighborhood where houses are being built, there's often a lot of sawdust and pieces of wood and nails lying around. That's kind of like what you look for when you look for evidence of newborn planetary systems. You're looking for the debris left over from the formation. And so after maybe 150 million years, after the birth of a star, we get to the point where we have mature exoplanets. So this is just one example, artist rendition again, 55 Cancri E, which is kind of a lava planet. It's so hot there that the rock is liquid, and there's such an intense amount of radiation hitting that star that it's literally sublimating away in material, so it has almost like a comet-like tail that's been observed. So these are great artist renditions. How do we find planets like this? Well, the most obvious way we might think of would be to directly image such a planet. So we're going to zoom in here on Beta Pictoris, which is the second brightest star in the constellation of Pictoris. And it's a very bright star. So what do? We use technology coronagraphs to block out the light from the star, to see the faint stuff very close in next to the star. An analogy that's often been used is that if I put a telescope in New York City, and then I put a searchlight, one of those searchlights that advertises a sporting event or some type of big event, and if I put a firefly right next to that searchlight, seeing planets around nearby stars is the equivalent of seeing that firefly next to the searchlight in Los Angeles looking from New York. So it's not an easy task. And Scott Gowdy, who's one of the scientists in the field, actually did the math on it. He's like, nope, that's actually 10 times too easy. It's actually 10 times harder than that. For every 10 billion photons you get from a sun-like star, you would get one from an Earth-sized planet in an Earth-like orbit around a sun-like star, which is quite remarkable. But nonetheless, that's what we're trying to do. And in this example I showed you, Beta Pictoris, this was a star that was known to have a debris disk. It's been known since the 80s to have a debris disk. So we went looking for evidence of planet formation, and in 2003, they saw a speck of light next to that star that they thought might be a planet, and they went and looked a couple years later, and it was gone. And then a couple years later, in 2007, it showed up on the other side. And so this was one of the first dozen or so directly imaged planets. This one happens to be a Jupiter analog. I think it's about 8 times the mass of Jupiter, orbiting at a similar distance from its star as our Jupiter does around our own. And here it is. This was actually the best video that's ever been taken until recently of a planet around another star. But this is the technique where we can find and block out the light from the star. That wasn't a black hole. We're blocking the light out from the star to see the faint glow of the planet next to it. Since then, we've found this fascinating system, HR 8799. And we've been watching it since it was discovered. Christian Marwan discovered this system. We've actually been able to now see the planets moving around the star on a human time scale. And so we know these are bound to the star. And these are all super Jupiters, and this happens to be a really young A-type star about twice as massive as our sun. And it has, because it's so young, the planets are still hot. They're glowing from the heat of their formation. And so they're easier to see. Instead of 1 out of every 10 billion photons, it's more like 1 out of every million photons, a little more than that, I think. And it's quite a remarkable discovery. So that's kind of the way you would think that you would find planets around other stars the easiest, but in fact, it's quite hard. And it's not going to be until we have a space mission, I'll probably wrap up my talk talking about that, to perhaps image another Earth, hopefully sometime before I retire. The most successful method for finding planets around other stars, we have two of the world's experts here in the room, Dr. Plavchan and Dr. Collins. So the transit method. Transit method is fairly easy to visualize. How many of you got to see the solar eclipse a year ago? Yeah, totality, did that go through No, it went through Tennessee.
It was 100 miles away.
100 miles
60
outside
miles away.
from here?
Yeah.
Still, nice easy trip. I drove from Virginia to Tennessee to see it. But basically, transiting planets, the basic idea is we're seeing a transit. It's just like a solar eclipse. We're just talking about a planet around another star. And this may sound relatively straightforward. And you might ask yourself, why did it take us so long? The first transiting planet was discovered in 1998 using a 4-inch diameter telescope. Well, I think, didn't Newton build a 4-inch reflecting telescope in the 1600s? How big was his reflector? Smaller than that? But it's certainly been a few centuries since we've been able to build 4-inch telescopes. And so what took so long to find planets around other stars, with the first one being found, or believed, the first one being believed around the main sequence star being discovered in 1995. Well, we'll talk about how they discovered it, but the Nobel Prize was just awarded this year in physics for the first discovery of a planet orbiting a sun-like star that everyone believed, and that was 51K. We'll come back to that in a minute. The reason why it took so long is because it's a precise measurement. It's only a small change in brightness.